So are you able to see my screen?
Yes, sir.
Okay. So this is what we have discussed, how to estimate friction factor, heat transfer coefficient and mass transfer coefficient. So already we have covered flow or flat plate, which is covered in chapter number 4. So for point 2, chapter number 4, we'll discuss about flow or flat plate. Page number are 60 to 66. This is what we have covered. And as I told, there is no theoretical background, theoretical derivation for this equation. All these equations are experimentally uh, 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 fitted equation, experimental data fitted into polynomial equation using some dimensionless number. So this is what remaining thing is there, flow past single sphere. So which is from page number 60 to 78. So friction factor, heat transfer coefficient and mass transfer coefficient. So some of the correlations are given. Then we have flow normal to single cylinder, friction factor, heat transfer coefficient, mass transfer coefficient. Then flow in a circular pipe. Then flow in non-circular duct. Some information is given related to this, how to handle if I have a flow in a duct, but it is not circular, non-circular duct. Then flow through packed bed. So because in catalytic reactors and all, and so packed bed is very commonly used in chemical engineering. So that is what this it is discussed. So these are the some of the important engineering correlation which is discussed in chapter number 4 of this book actually. So which book? Just hold on. This is chapter number 4. So already we have discussed this initial 4.1 and 4.2 also we have discussed. So this is what engineering correlation we have discussed for flow or flat plate. And then these are all problems we have solved. So and now what is you need to do is you need to study remaining part of this estimation of engineering correlation, not estimation using engineering correlation. So as such, there is no derivation, fundamental derivation is given. Direct equations are given, and you need not to worry about that because these are all experimentally fitted equation. So there is no logic behind this. Why this Reynolds number is between 2 to 500? Why it is not between 2 to 10,000 or so? Why after this thing equation is changing? All they have observed the experimental data and try to fit the data in a form. Friction factor is a function of Reynolds number. Then here Nusselt number is a function of Reynolds number and Prandtl number, and then Sherwood number is a function of this Reynolds number and Schmidt number. So similarly, this is flow over a sphere. This is for momentum transfer. So you can see these are the engineering correlation and solved problems are there. So this will be, you can say, assignment for you to go through all these engineering correlations, solve problem, and then this heat transfer correlation. You can see Nusselt number is a function of Reynolds number and Prandtl number. Everywhere you will find Nusselt number is a function of Reynolds number and Prandtl number. So similarly for mass transfer, you can say Sherwood number is a function of Reynolds number and Schmidt number. This is flow over sphere. So you can see for there are more than one correlation. You can see mass transfer correlation, flow over sphere. So somewhere Sherwood number equals to 2 is there. So some limitations are there. So then Ranjan Marshall correlation is there. Then Frostling correlation is there. Then this treble correlation is there. So many correlations are there. So according to given situation, then flow normal to cylinder. So these are the correlation for friction factor, and these are the correlation for heat transfer. Nusselt number is a function of Reynolds number, and most importantly, so flow through pipe. Okay, this is for mass transfer, and this is flow through pipe. This is most important for chemical engineering. So some of the information for momentum transfer is given. So these are the correlations. So you can see this correlation. Sometimes it will give this thing also. You can say Moody's chart. Okay, determined from Moody's chart 1944. So this year indicates where this actual paper, research paper related to this is published actually. So this is for momentum transfer, and you might have been used this Dittus-Walter correlation, which is very famous heat transfer correlation. So this is Dittus-Walter correlation. Dittus-Walter published this correlation in 1930. Nusselt number equals to 0.023, Reynolds number raised to 4 by 5, Prandtl number raised to n is 0.4 for heating and 0.3 for cooling. And these are remaining limitations. So this is you can say Dittus-Walter Sidertate. So sometimes you can use both. So that your choice. So you can use either this or this. So based on limiting value, you can use the limiting value for design thing actually. So likewise, you need to go through whole chapter number 4, solved, unsolved. First, go through all the engineering correlation and solve all the problems. Okay, write the notes on this chapter number 4, solve all the problems, and then try to solve unsolved problem also from this chapter number 4. So this will be the you can say portion which will be related how to estimate heat transfer coefficient, mass transfer coefficient, and momentum transfer coefficient. And previously also I told that these are not the only engineering correlation available. There are thousands of engineering correlations available. If you go in literature, so you can get many engineering correlation, but we'll stick ourselves at least for this fundamental transport phenomena, your syllabus, only to this whatever information given in chapter number 4. Otherwise, there is vast data available. Okay, so we'll stick to only chapter number 4 only. Chapter number 4. So whatever given in chapter number 4, that will be that you need to study properly. So you need to write the assignment on this. I will spell out the details of the assignment. So there are some unsolved problems also. All these unsolved problems are based on whatever solved problems are there. So just this will give you flavor. This will give you flavor how to use, how to get the heat transfer coefficient, mass transfer coefficient, and friction factor, and how to use for various design problems. That is what given in the chapter number 4, and this is everything is for assignment for. So that is what I am going to cover in a class, and remaining thing will be assignment for you. Is it clear for everybody? So these are the outline of that content actually. How to estimate friction factor, heat transfer coefficient, and mass transfer coefficient. So flow past flat plate already we have covered. Then flow past single sphere, flow normal to cylinder, flow in a cylinder, then flow in non-circular duct, and flow through packed bed. So this will be all solved and unsolved problem, and theory related to this. That is what will be their for assignment. Only this we have covered in a class, and remaining just use the equation, solve the problem. Use the equation, solve the problem. So only the thing is, while solving the problem, at least you will get to know that how many engineering correlations are there. So only engineering correlation are not important. Along with engineering correlation, their limitations are also as important as that equation. That is what. So you cannot use Dittus-Walter correlation for flow or flat plate. That is for sure. Everybody should know that whatever which system it is applied for, any relation. And moreover, some of the engineering correlation you will find with same name. So if you go like Cedar-Tate correlation, okay. So I will show you. So this is okay, friction factor. Whittaker correlation is also there are more than one correlation actually. So just I will see. Okay. So You can see this is the Whittaker correlation. So for which system it is applied for? This is applied for flow over sphere. Okay, this Whittaker correlation, Nusselt number equals to 2 plus zero point 0.4. So, and these are the limitation, and this is for flow over sphere. Okay, heat transfer from the sphere when there is a flow over sphere. Now let us see whether we have a similar Whittaker correlation. So this is Whittaker. You can see now. This is actually Whittaker correlation, and this is for what? This is, you can say, flow normal to single cylinder. So Whittaker is there for normal to single cylinder. Okay, this is the flow normal to single cylinder. So this is what engineering correlation is there. So this is flow normal to single cylinder, and that was flow over a cylinder. Then you can see, and then again if we have something, actually this is application, and again you can see this is flow through pipe. Okay, same Whittaker has given a correlation flow through pipe. Almost he has given for everything. So flow over a sphere, flow normal to single cylinder, flow through pipe. Same Whittaker has given a correlation in same paper, but these correlations are different. So this is also called as a Whittaker correlation. 4.4, there is one equation which is also called as a Whittaker correlation, and 4.3 also there is a Whittaker correlation. Let us see whether we have some more Whittaker correlation. Yes, there is a Whittaker correlation. No, that this is same flow through pipe only actually. Correlation pack bed. Again, pack bed is also there is a Whittaker correlation. So you can see, so Whittaker 1972, he has given a four engineering correlation which is listed in this book. What are these engineering correlation? Flow over a sphere, flow normal to cylinder, then flow through pipe, and flow through packed bed. So these are the four engineering. So Whittaker correlation with there is it is not the thing that there is only one equation. So this equation as well as whatever the limitations of this equation that you need to remember. Limitation will start from, so for which is system applied for. What is the range of Reynolds number? What is the range of Prandtl number for heat transfer? So for momentum transfer, what is the range of Reynolds number? For mass transfer, what is the range of Reynolds number, and what is the range of Schmidt number? So this is what the, you can say, brief about this engineering correlation. So hope this is clear to you. Anybody has any doubt over this? Okay, then now we will start next part. So this is what we are going to start today. So as it is concluded a couple of classes before, these are the most important parameter which will govern heat transfer, mass transfer, and momentum transfer. First of all, this friction factor, heat transfer coefficient, mass transfer coefficient, viscosity, thermal conductivity, diffusivity, and profile equation for velocity, temperature, and concentration. So how to estimate this? Already we have covered engineering correlation. Now we will go evaluation of transport property. These are also, you can say, semi-engineering correlation. Partial theory is there, partial experimental observation is there. They have combined this together. So some equation are purely engineering correlation, some equation are purely empirical equation, some equation are some data is in the form of graph, empirical graph, and there is some equation which is derived from a first principle theoretical derived equation for estimation of viscosity, thermal conductivity, and diffusivity. Why there is a theoretical, some of the equation will have the theoretical background for estimation of, because these are the property of material. I can say viscosity of air, viscosity, thermal conductivity of copper I can say. diffusivity of nitrogen in oxygen, that I can say. It depends upon material. It doesn't. So viscosity of air when flow through pipe is not different when flow normal to pipe. Viscosity will be same. Viscosity will not vary. So this is the property of material, and which will have some theoretical input. Okay. Some theoretical input. So viscosity, as you know, so if we discuss the velocity gradient and try to correlate with the momentum flux and all, so whatever be the proportionality constant, that that is a viscosity, and definition of viscosity says that it is tendency, okay, tendency to resist the flow. So higher the viscosity, lower fluidity will be there in a fluid. That is definition. Thermal conductivity. So higher the thermal conductivity, it will help to conduct the heat at faster rate. Similarly, diffusivity. Higher the diffusivity, higher will be the flux. Okay, kind of you can say transport will be higher. That is what there is a some theory involved in this. So some semi-empirical and empirical correlations will be using for estimation of this viscosity, thermal conductivity, and diffusivity. These already we have covered: friction factor, heat transfer coefficient, and mass transfer coefficient. Maybe today and tomorrow's class we will cover this, and then we'll move on to remaining part of transport phenomena. Will be everything related to viscosity, temperature, and concentration, how to get the profile equation for this. Okay, so viscosity. So we'll start with the viscosity, and this is first empirical graph. Okay, again, this is not a theoretical graph, this is empirical graph. People have done thousands of experiments, and some people have compiled all the data, and they try to put the information in one graph. Okay, so what is this one graph is? So on y-axis there is a reduced viscosity. Reduced viscosity, this is the ratio of viscosity to viscosity of compound at critical stage. Okay, reduced viscosity. On x-axis it is reduced temperature. So on x-axis it is reduced temperature. So this is the ratio of temperature, given temperature, to the a critical temperature of the material. Critical temperature of the material. Hope everybody knows the critical property. Every compound will have some critical temperature and pressure, and then they have observed. So this is the variation of critical pressure. This is the variation of critical pressure. So at given critical temperature and critical pressure, this will be the this reduced viscosity. So this is again reduced pressure. This is reduced pressure. Reduced pressure is a ratio of pressure to a critical pressure of the compound. So at given reduced temperature and reduced pressure, you can get. So say this is the value. Say and this is logarithmic scale. You need to understand this is the logarithmic scale. So say at reduced temperature 2, so this is the reduced temperature 2, and then if I move on this reduced temperature 2, and somewhere here, so this is reduced so this you can see, this is the reduced pressure 10. This is reduced pressure 10. So this is reduced pressure 10. So if I go here, so reduced viscosity will be somewhere close to 1.9. Okay, close to 1.9, in fact more than that actually, because this is logarithmic scale. So once I get this reduced viscosity, I can estimate the critical viscosity, and there are equations available to get the value of critical viscosity. Empirical equations are available, hence I can get this viscosity values. Okay, so anybody has idea what is critical temperature and pressure? Anybody has idea?
So it is that temperature beyond which the liquid and vapor phase cannot be differentiated.
Very good. So, and this is the property of material. Like every material will have boiling point. You think of copper, copper will also have some boiling point. Copper will also have melting point. Similarly, water. Water will also have boiling point. Water will also have melting point. So 0 degree Celsius is a melting point of water. So, and 100 degrees Celsius is a boiling point of water. So this melting point, boiling point, similarly, there is a critical point also there for every compound. This is true for every compound will have critical temperature and pressure. So this diagram explains. Okay, so this is what you have considered till now, and this is applicable almost in 99% of the processes. Okay, because our operating temperature and pressure will be in this range only. It is where very rarely will go in this range. Actually, this is very high temperature and high pressure, so hence this is not covered in many of the books. Okay, only we will cover is, so this is liquid, gas and solid, and here we'll have triple point. So this triple point, and this is boiling curve is there. Okay, boiling curve is there. So here this line indicate the equilibrium between liquid and gas, this line indicate the equilibrium between solid and liquid, and this line indicate the equilibrium between solid and gas. This is called as a sublimation line. This is called as a sublimation line, and this is called as a vaporization line, and this is called as a melting line. So melting solid to liquid. Okay, so likewise you will have this thing. So what is happening here? Here we will have gas, here we will have liquid. So on this vaporization line there is a clear separation between liquid and gas. Liquid is evaporating and I am getting a gas, and I will have two phase system. One is a liquid, one is a gas. But as I am increasing the temperature, increasing the pressure, so what is happening on the density of liquid and density of gas, effect of temperature and pressure. I am increasing the temperature. So here I am increasing the pressure. So what is happening? Increasing the pressure doesn't affect the density of the liquid, because liquids are said to be a incompressible fluid, or compressibility of the liquid will be very very low. So increasing in pressure doesn't have any effect on a density of the liquid, but increasing in pressure the density of the gases will increase. So increasing the pressure, so as I'm moving on this line, the density of the gases are increasing. Okay, density of the gases are increasing while density of the liquids are remains unchanged with pressure. Okay, say I am moving on this line, density of the liquid will remain unchanged, while if I look temperature axis, so density of gases kind of remain unchanged with the temperature. Unchanged or little effect will be there on a density of gases, effect of temperature. But liquid will have large effect of temperature variation, and density of liquid will reduce. And in some cases, in fact, density of gases will also increase with the temperature, because as we increase the temperature, this kinetic energy of the gases will increase, and it will lead to be an increase in density, but that is very negligible as compared to reduction in a density of liquid. Okay, there also kinetic energy of molecule plays a role. So so as we increase the temperature, density of liquid is decreasing. As we increase the pressure, density of gases are increasing. So if I am simultaneously increasing the pressure and temperature, there is some point at which you will get that density of liquid will be equals to density of gases. As soon as I get this, so there will not be any clear differentiation between two phases, liquid and gases, and I will get a new phase. This is also phase actually, which is called as a supercritical phase, and this point is called as a critical point. So every compound will have some critical temperature and pressure. For example, for water, it is something around 450 degrees Celsius and 273 atmosphere. For carbon dioxide, it is 72 atmosphere and 32 degrees Celsius. For every compound, you will have this critical temperature and pressure, and I can estimate the property at this critical temperature and pressure. So critical temperature and pressure is the property of compound. Every compound will have some critical pressure, critical temperature. This is point actually. So critical temperature, this will be given, this will be given. So at given temperature, I can calculate reduced temperature, I can calculate reduced pressure, and then using this empirical graph, this is empirical graph, this is empirical graph, I can get a reduced viscosity. Now only the thing is how to get this value of reduced viscosity, critical viscosity. Okay, so for estimating viscosity at critical condition, these are the empirical relations used. Okay, critical viscosity equals to 61.6 molecular mass, critical temperature raised to half multiplied by critical volume raised to minus 2 by 3, or critical viscosity equals to 7.70 molecular mass raised to half, critical pressure raised to 2 by 3, and critical temperature raised to minus 1 by 6, where this critical viscosity is in micropoise. Okay, critical viscosity is in micropoise, pressure is in atmosphere, temperature is in Kelvin, and this critical volume is in centimeter cube per gram mole. Okay, temperature is in atmosphere, pressure is in atmosphere, temperature is in Kelvin, and I will get a viscosity in micropoise. That is what you will see. Sometime in empirical relation, it will not be a consistent unit wise. There will not be unit consistency in empirical relation, because these are all experimentally data put together and fitted in this equation and got this constant. So I don't know what is the this unit of this constant. This is in atmosphere, this is in Kelvin, and this is in micropoise. Okay, so accordingly you can get the constant. So you need to remember empirical equation as it is. You need to remember empirical graph as it is, and because these are all experimental observation put in the equation. That is what. So this is how I can get a critical viscosity, and using this empirical graph, I can get a viscosity at given temperature and pressure. So critical, if I have mixture, there is a you can say a mixture of compound is there. So how to get the critical so individual critical pressure will be there. So this is wetting factor. You use mole fraction into mole fraction of that compound alpha into critical pressure of that compound alpha. Summation of this, I will get a critical pressure. Similarly, critical temperature also, and I can get critical viscosity also. I will get the viscosity of pure compound using this, and then using mole fraction as a wetting factor, mole fraction multiplied by critical. This is just, you can say, arithmetic. Okay, algebraic sum. Okay, algebraic summation used to get the property of mixture. So using mole fraction as a wetting factor, so I can get a critical pressure of a mixture, critical temperature of a mixture, and this is critical viscosity of a mixture. And this is not universally true. This is applicable when you are using these only for estimation of viscosity, because you can see this critical this is algebraic sum used. Okay, algebraic sum used. Logically, if you go, this temperature is not you can say additive property, but here algebraic summation of critical temperature is used. So there will be some ifs and buts in all empirical relation, but whenever you are using this empirical correlation, that an empirical graph, so this is the property how you can get the critical pressure of the mixture, critical temperature of the mixture, critical viscosity of the mixture. So you need to remember. So only this is 100 times I am telling that only remembering this empirical equation is not important. It is important to remember all the situation, how these empirical relations are derived, and what is the limitation of empirical correlation. Otherwise, if you use this everywhere, certainly you will get some wrong readings. Okay, because fundamentally this is how this experimental observation, while doing experimental observation, these are the formulas used that will give the limitations for this equation. So where to use that equation? This is okay. How to get the viscosity? So once I have this viscosity and critical viscosity, reduced viscosity and critical viscosity, I can get the viscosity of the material. Okay. Okay. Get the viscosity of nitrogen at 50 degrees Celsius and 854 atmosphere. Molecular mass of nitrogen is 28 gram per gram mole, and critical pressure of nitrogen is 33.5, and critical temperature of nitrogen is 126.2 Kelvin. Okay, 126.2 Kelvin. So estimate the viscosity of nitrogen at 50 degrees Celsius and 854 atmosphere. Yeah, roll number 31. Roll number 31.
Yes, sir.
So what is the value of reduced temperature and reduced viscosity? What is the definition of reduced temperature?
Definition. Gas divided by critical temperature.
Gas divided by. So what is gas divided by critical temperature?
Temperature of a gas
Yeah.
divided.
What will be the reduced temperature for a given case?
Reduced temperature. 126.2 Kelvin.
Reduced temperature.
1 2.56
How you have got this 2.5?
from the TR.
Huh? From the TR, how you got this TR? Just looking at the slide which was given last year will not help you actually. You need to understand. Just you want to refer the slides which was given to student last year and we are giving the answer. That will not improve your understanding. You need to, when I am explaining, otherwise, what is the point in conducting these classes? So already I have recording also, last year's recording. I can give that recording. So whether you was concentrating on a class. So how to get TR?
273.2 plus 50 by 126.2.
How 55? From where you got 55?
50, sir.
50. So how to, so that is given the temperature of gas is 50 degrees Celsius. So convert that in Kelvin to 273 plus 50 and divided by critical temperature. So you will get a reduced temperature. What is there is nothing very great in that actually. You need to observe the data and just concentrate what I was telling actually. Just a couple of slides before I explain. What is critical at temperature, pressure?
1 minute, sir. 25.5.
25.5. How you got 25.5?
854 by 33.5.
Yeah. So everything is given actually. What is point in just looking at the slide which was given last year? So and now, you will get this reduced value of temperature, reduced value of pressure. So using that, you can get a reduced value of viscosity using empirical graph, and there you need a critical value of viscosity. So this is the using this empirical correlation, you can get the critical value of viscosity. So critical pressure, critical temperature, molecular mass, everything is given. So you can calculate the critical value of viscosity. So what is the critical value of viscosity? So you can substitute in this equation. Here roll number 50, Rashmi.
Yes, sir. So it will be 7.7 into 5.29. So just 1 minute into 2.24 into 10. So it is coming around 70.7.
70.7 micropoise. You substitute this molecular mass equals to 28. Critical pressure is in atmosphere 33.5 and critical temperature 126.2 Kelvin here, and use this equation.
Yes, sir. So I did that.
So you got 70.
No, sir. So it is 190.
Yeah, 190 micropoise. Okay, so now you can see this is reduced temperature. Reduced temperature is 2.56. So temperature is given and critical temperature is given. Similarly, pressure is given and critical pressure is given. So reduced temperature and reduced viscosity. Now using this empirical graph, now here you can see how many parameters are there. So this is reduced temperature, temperature divided by critical temperature, is pressure divided by critical pressure, and here I have reduced viscosity, viscosity divided by critical viscosity. So I can get from data book critical temperature and critical pressure is available in so many data book. So these two parameters are available. So using this critical temperature and critical pressure, I can estimate critical viscosity. So these three parameters will be available in data book, you can say. This is not available in data book. We are using some empirical correlation. So that in data book, you will get this critical temperature, critical pressure, and molecular mass also you can get from data book. So this hence I can get critical viscosity also, and remaining is viscosity, pressure, and temperature. Out of these three, if two is given, I can estimate third one using this empirical graph. So here temperature was given, pressure was given, so I can estimate viscosity. If viscosity is given and pressure is given, so I can estimate the temperature of the fluid. If temperature is given and viscosity is given, so I can estimate the pressure. So likewise, you can use this empirical graph. Okay. Now here, what is the reduced temperature? Reduced temperature is something around 2.6 and reduced pressure is something around 25. Okay, something around 25. So somewhere here I will get a point. Okay, somewhere here I will get a point. So using this, so reduce temperature and reduce viscosity, I will get a reduced temperature and reduced pressure, I will get a reduced viscosity. So here somewhere I will get a reduced viscosity value. Using this reduced viscosity value and critical viscosity value, I can get the value of viscosity. Okay, so this is what you can see from the figure. The reduced viscosity is 2.39. So reduced viscosity is 2.39. So here somewhere, so this is reduced temperature. What is reduced temperature? Reduced temperature is 2.56 and 25.5. 25.5, 2.56 and 25.5. Somewhere here this point will be there. So this using this actually 25, this is 25. So you can extrapolate this. This is 10, 25, and you can extrapolate this. Somewhere here you will get. So using this, if I extrapolate, so it will be 2.39, and this is logarithmic scale. So this is logarithmic scale. So, if you want very accurate answer for your design purpose, you can digitize this graph also. If digital graph is available, sometimes this data will also be available. You can plot this graph. If this graph is not available and you want to digitize using this JPG format of the graph, there are many softwares available which can be used for digitizing this graph. So digital information, so you can get the what is exact value here, xy, and this value actually what is the value of xy, what is the value of xy, exact value that can be done. So here somewhere I will get, and this reduced viscosity, according to this it is something around 2.39. Now I got this thing actually, critical viscosity. Critical viscosity is there, so I can get the value of viscosity. So what is the value of viscosity? What is the value of viscosity? Yeah, roll number 67, Mayank. Roll number 67, Mayank. Roll number 49, Jayant. PT 18, roll number 49. Jayant, roll number 49, Jayant. Jayant, are you able to listen to me? Just switch on your mic. Yeah, all CR, please convey message to this Jayant. Better you drop the course. Okay. So I'm not going to call you again. Yeah, roll number 67, Mayank. Are you able to listen to me? Whether I am audible?
Yes, sir, you are audible.
Okay, Mayank. Very good. Roll number 86, Prashant.
Yeah, hello.
What
Hello,
is the
sir.
value of viscosity?
So viscosity I got sir 4.51 into 10 to the power minus 4 poise.
Okay, 400 something points. Okay,
Yes,
400 into some 10 raised to minus 6 actually. So,
yes, sir.
yeah, 452 into 10 raised
4
to
point.
minus 6. Yeah, 4.5 into 10 raised to minus 5 you told. Correct actually. So
Yes, sir.
this is how you can use this empirical graph. So just I will brief. So there are 6 parameter in this. This is temperature, given temperature. This is critical temperature. This is pressure. This is critical pressure. This is viscosity, and this is critical viscosity. So this data you can get from data book. This is critical temperature, critical pressure. You can get from this data book. Similarly, molecular mass also you can get from data book. So certainly you can get this value from data book, critical viscosity. So this critical temperature, critical pressure, and critical viscosity can be obtained from data book. Now remaining is temperature, pressure, and viscosity. Out of these three, if two is given, I can estimate third using this empirical graph. Okay. So if say viscosity and pressure is given, so I can estimate corresponding temperature using critical, that empirical graph. If temperature and pressure is given here, temperature and pressure is given, so I can estimate the viscosity. If viscosity and temperature is given, I can estimate the pressure. So this is clear how to use this empirical graph. Okay, now this molecular theory of a viscosity of gases at low density. So this is the equation which is derived using kinetic theory of the gases. So most importantly, assumption. what they have assumed for deriving this equation is they have assumed a molecule of gases as a solid spherical ball. Every molecule of the gases is assumed similar to solid spherical ball with the non-interacting forces between them. So one molecule of gas is not interacting with another molecule of gas. Forces between these two molecules of gases are negligible. That is why this is low density. So using kinetic theory of gases, then you can get the velocity also, velocity and different fundamentals are there, and they have consider this shear stress between these two non-interacting particles, spherical particle, and they got this equation. Okay, so we are not going to go in details of this equation. So viscosity equals to 2 by 3 under root of mkt divided by pi d square equals to 2 by 3 pi under root of pi mkt divided by pi d square, where k is a Boltzmann constant. Okay, k is a Boltzmann constant. D is the diameter of the molecule. So, because sphere of diameter of the molecule, H2O will have some diameter, nitrogen will have some diameter, air will have, the oxygen will have some diameter of the molecule. It is considered actually. So this can be estimated by using interatomic distance, and this will be there in various data books. M is a mass of the molecule, molecular mass of the molecule. Mu is a viscosity, and dimension is mass divided by length and time. Mass divided by length and time. So this is molecular diameter in length. L stands for length. Mass is in m, so kg, gram accordingly. So this is the viscosity, this mass divided by length and time, and T is the absolute temperature measured. So this is stands for T. It is measured in Kelvin. Okay. So this is dimensionally consistent equation. If you go and check, so you will get dimensionally consistent equation. So this is the equation applied for low density gases only, because assumption. So it is assumed that these two molecules will have negligible force of interaction between these two molecules, and they have derived. So I am not going to go in details of derivation. So it needs a whole kinetic theory of gases and intermolecular, you can say, statistical mechanic information. Okay, so huge information is needed behind this deriving this equation. Most importantly, how to use this equation, that is what we need to concentrate on this. So you need to remember this. So but this is not an empirical equation, this is theoretically derived equation. This is the theoretical derived equation. As I told, there are few equations which are available, which are derived from first principle theoretically. Okay, this is one of the equation. Okay, this is one of the equation. Viscosity equals to 2 by 3 under root of mkt pi d square. This is just a rearrangement. Okay, same equation is there, so just a rearrangement. So, and this is the Maxwell equation. This is used for polyatomic gases, and when density of gases are larger. Okay, when density of gases are larger, molecule of gases are again considered to be a spherical, but their distance between these two molecules is considered to be a lesser, so that they are interacting. So there will be interacting force, and for deriving this equation, again statistical thermodynamics has more important actually. More input is taken from statistical thermodynamics, and Maxwell has derived this equation. And these are the collision diameter, collision integral. These are the information from statistical thermodynamics. Okay, statistical thermodynamics. This collision diameter is measured in angstrom, temperature is measured in Kelvin, and viscosity is in gram centimeter per second. So Maxwell equation can be used for viscosity of polyatomic gases as well as monoatomic gases also with a higher density. If molecules are closely in close, this thing actually close distance, molecular density is higher. So more molecules are there in lesser volume. That time also this Maxwell equation is better. Okay, Maxwell equation is better. So most importantly here, so you can say for viscosity of gases is directly proportional to under root of temperature. This information is largely used in chemical engineering in many purposes. Many design problem involve viscosity are given at one temperature and you need to estimate the viscosity at another temperature. That time this information. So viscosity is directly proportional to temperature. So as far as this transport phenomena is concerned, so what is the take home message? So you can consider this viscosity is directly proportional to under root of temperature with some constant, okay, collision diameter, collision integral and all. So using this information, so whether let us see whether we can solve this problem. The viscosity of carbon monoxide at 1 bar, okay, hello, बोलिए. Okay, so this is carbon monoxide. Okay, carbon monoxide is there at 1 bar and 27 degrees Celsius. So viscosity is there given 0.00015 Newton second per meter square. Estimate the viscosity at 1 bar. Temperature is same and 273 Kelvin. In fact, this is the numerical asked in GATE exam for 1 mark. Okay, this is the numerical asked in examination for 1 mark, and moreover, this Maxwell equation or this kinetic theory of gases equation, okay, molecular theory of viscosity of gases equation is the basis for solving this problem. Actually, only the thing here you need to use the relation that viscosity is proportional to under root of temperature. Okay, yeah, roll number 91. 91. I'm not able to hear you.
Yes, sir. Hello, sir.
Yeah. How to solve this problem?
Sir, mu is directly proportional to 150. So we can calculate two different temperature and pressure is constant.
Yeah. So you can substitute the information. So you can use any of these equation, either Maxwell theory or kinetic theory of gases. Okay. So in both here also viscosity is directly proportional to under root of temperature. Here also viscosity is directly proportional to under root of temperature. So combining this, viscosity is directly proportional to under root of temperature. So mu1 is given, T1 is given, T2 is given, calculate mu2. Okay. So this mu T1, it is given, and this is T1. This is temperature T1 is given. This is mu T2, and this is T2. T2 is given. So you need to estimate T1. So moreover, this temperature is in Kelvin. Okay, that you need to remember. So convert that temperature in Kelvin and then get the value of this thing actually. Viscosity at temperature T2. So what is the viscosity? Yeah, roll number 91. What is the viscosity at 327 degrees Celsius?
2 minutes, sir. Calculating.
So anybody got the value can write the value in chat box. Yeah. So it is 2.1 into 10 raised to minus 5 Newton second per meter square. Newton second per meter square. So this is Kelvin. Okay, temperature is in Kelvin. So this is T1. Okay, so this T1 is taken to be a 323 Kelvin. So the T1 is 600, this is 300. So it is 2.21 into 10 raised to minus 5 Newton second per meter square. So hope you understood this, our strategy. How to deal with estimation of this viscosity, thermal conductivity and diffusivity. So we are not going to go in details of derivation of this equation. Only will touch upon few fundamental equation which can be used for estimation of this, and use this equation for the purpose. So at least you will know that how to estimate this viscosity. And same thing we have done for transfer coefficient also, heat transfer coefficient, mass transfer coefficient and momentum transfer coefficient. Same thing we have done. So we have not gone in details of these equations. So only the thing is we need to use the equation. At least you will have some idea how to estimate heat transfer coefficient, how friction factor you can obtain for your system, how mass transfer coefficient can be obtained. Same strategy we will apply for this viscosity, thermal conductivity and diffusivity also. So just we'll touch upon the slide, whatever be the important equation available for this estimation, and we'll move on. So this is all about what we are going to cover in today's class. We'll continue this discussion in tomorrow's class, tomorrow at 11 o'clock. If you have any doubt, so you can stay back. Otherwise, you can go for next class. Thank you very much.